Beyond the familiar beauty of stars and galaxies lies a stranger, darker side of reality. The more we look, the more unsettling it becomes. Why do some galaxies behave as if they're haunted by invisible forces? Why do ancient stars contain the wrong ingredients? And why does the fabric of the cosmos hum with energy from events we can neither see nor explain? This is not the universe you learned about in school. This is the universe at its most bizarre, where light moves faster than it should, where shadows are cast by things we can't find, and where long-held theories tremble under the weight of new evidence. So buckle up, because the deeper we go, the weirder it's going to get. Ghosts of the Big Bang, the cosmic neutrino background.
Long before galaxies formed, before stars began to shine, and even before atoms came together, the universe was a hot, dense ocean of particles. In those first moments after the Big Bang, everything we know today was squeezed into a space smaller than the tip of a needle. Temperatures soared, and matter as we understand it today couldn't yet exist. Instead, the cosmos was filled with a soup of the smallest particles, zipping around at incredible speeds. Among them were neutrinos, tiny, almost weightless particles that barely interact with anything. These are sometimes called ghost particles, and for good reason. Even now, more than 13 billion years later, these ancient travelers from the dawn of time are still passing through us. We can't see them, we can't feel them, but they are there, moving through our bodies, our planet and our skies, as silent witnesses to the birth of everything.
When scientists talk about leftover signals from the Big Bang, most people think of the cosmic microwave background radiation, or CMB. Discovered in 1965, the CMB is the faint glow of heat left behind from the moment the universe cooled enough for light to travel freely. It's like an old photograph of the universe when it was just 380,000 years old. But the cosmic neutrino background is much older. It formed just 1 second after the Big Bang. Back then, the universe was so dense and so hot that particles were constantly colliding. Neutrinos were being created and destroyed all the time, but as the universe expanded, it cooled, and when it cooled enough, neutrinos stopped interacting with other matter. They slipped free and began traveling through space on their own paths. Ever since that moment, these ghost particles have been on a never-ending journey. What makes neutrinos so hard to detect is the fact that they rarely interact with other particles. A beam of light might bounce off a wall, a stream of electrons might be stopped by a sheet of metal. But neutrinos will pass straight through almost anything, even entire planets, as if nothing is there. Trillions of neutrinos pass through your body every second, and you don't notice them at all. That's how invisible they are. But because they are so difficult to detect, finding proof of the cosmic neutrino background has been one of the greatest challenges in science. Unlike the cosmic microwave background, which can be mapped with radio telescopes, the cosmic neutrino background leaves only the faintest clues of its presence. Scientists believe that by studying these ancient neutrinos, we can learn about the very first seconds of the universe. Before neutrinos broke free, the universe was a place of extreme energy and chaos. Forces we now see as separate, like gravity and electromagnetism, may have been part of the same force. Matter was not organized into atoms, molecules, or anything we would recognize. Everything was raw energy and fundamental particles. But when neutrinos decoupled, they carried with them a snapshot of that early time. If we could capture even the smallest piece of that information, it would be like opening a time capsule sealed at the beginning of everything. So how do scientists try to find something so elusive? The answer is through clever experiments and indirect evidence. One method involves looking at how neutrinos affect the way galaxies and other large structures have formed over billions of years. Neutrinos may be tiny and light, but there are so many of them that together they have a noticeable effect on gravity across the universe. Their presence slightly changes the pattern of how matter clumps together. By studying the large-scale structure of the cosmos, scientists can look for the fingerprints of these ghost particles. It's like looking at ripples on the surface of a lake and figuring out what caused them, even if you can't see the pebble that made the splash. There are also experiments deep underground, shielded from other forms of radiation, that try to detect the rare moments when a neutrino might actually collide with an atom. These experiments are extremely sensitive, but the neutrinos from the cosmic background are so cold and slow now that capturing one directly is almost impossible with today's technology. They've been cooling for over 13 billion years, and now they are only a tiny fraction of a degree above absolute zero. They are, quite literally, among the coldest things in the universe. Even though we haven't directly detected these ancient neutrinos yet, their existence is almost certain. The math works out perfectly. The same physics that explains how stars shine and how particles behave also predicts that these neutrinos must be there. In fact, there should be around 300 cosmic neutrino background particles in every cubic centimeter of space. That means there are billions of them passing through even the smallest objects at any moment. They're everywhere, all the time. And yet, despite being all around us, they remain invisible, like whispers from the earliest moments of time. They remind us that the Big Bang's effects are still unfolding. Its energy, its particles, and its echoes continue to fill every corner of the cosmos. Though we can't quite catch it yet, the cosmic neutrino background holds secrets about where we come from, and maybe how it will all end. Transient lunar phenomena, unraveling the moon's fleeting mysteries. The moon is our closest neighbor in space, a familiar and steady presence. Its surface, marked by ancient craters and smooth plains, seems calm and unchanging. But every so often something strange happens. For just a few moments the moon behaves in inexplicable ways, bright flashes of light, unusual glows, shifts in color. These brief, mysterious events are known as transient lunar phenomena, or TLP for short. They don't last long, sometimes just a few seconds, other times maybe a few minutes, but they leave behind questions that have puzzled scientists for centuries. Stories of strange happenings on the moon go back a long way. In fact, the first known report comes from over 1,000 years ago. In 1178, a group of people in England claimed they saw a bright flash and a fiery glow on the moon's surface. For most of history, reports like this were dismissed as mistakes. Maybe people were just seeing stars or reflections or clouds playing tricks on their eyes. After all, the moon doesn't have weather like Earth does. There are no storms or shifting skies. It's a quiet, airless place. How could anything on the moon change, even for a moment? But as time went on, more and more people, including trained astronomers, began noticing these short-lived events. Through their telescopes, they would spot strange things: a quick sparkle on the edge of a crater, a reddish glow where there usually wasn't one, or a misty-looking patch that seemed to drift for a few minutes before disappearing. And they all described the same thing. These flashes and colors never stayed. They came and went as if the moon had secrets it only revealed when no one was expecting it. Scientists have spent years trying to understand what could be causing these mysterious moments. One idea is that some of these flashes are caused by tiny meteoroids, small pieces of rock from space, hitting the moon's surface. Unlike Earth, the moon has no thick atmosphere to burn up these space rocks before they hit the ground. Even a pebble-sized object, moving fast enough, can slam into the moon with so much force that it creates a small explosion of light. These impacts happen more often than you might think. In fact, during meteor showers on Earth, like the Perseids or the Leonids, scientists now watch the moon closely. Sometimes they catch these impacts on camera, recording brief, bright flashes that match the timing of the meteor showers. But not all TLP can be explained by meteoroids. Some of the events people have seen don't fit that pattern. They happen in the same places over and over again, even when no meteor showers are happening. One of the most famous spots is a crater named Aristarchus. For reasons no one fully understands, Aristarchus seems to glow or change color more than any other place on the moon. Observers have reported strange red, blue, or violet tints appearing there, lasting anywhere from a few seconds to a few hours. And these reports are not just from casual stargazers. Even professional astronomers using powerful telescopes have seen odd flashes and glows around Aristarchus. So if it's not always meteors, what else could it be? Another theory points to gas escaping from beneath the moon's surface. Unlike Earth, the moon doesn't have active volcanoes anymore, but that doesn't mean it's completely dead inside. Some scientists believe that deep below the surface there may still be pockets of gas. Over time, cracks or shifts in the lunar crust might let small amounts of gas escape. When this happens, the gas could briefly reflect sunlight in odd ways, or maybe even glow as it reacts with particles on the surface. If this is true, then TLP might be one of the last signs of activity on a world that most people assume is completely silent and still. There is also the question of dust. The moon is covered in a fine, powdery material called regolith. With no air to move it around, the dust just sits there. But some scientists wonder if sudden releases of gas, small moonquakes, or even temperature changes could kick up clouds of this dust. Floating just above the surface, these tiny particles might scatter light, creating the appearance of a faint glow or mist. This might help explain some of the soft, hazy lights that observers have reported over the years. Despite all these ideas, the truth is that no one completely understands transient lunar phenomena. We have theories and we have clues, but we don't yet have all the answers. What makes the mystery even harder to solve is how rare these events are. You can watch the moon night after night and never see anything unusual. Even the best cameras and telescopes don't always catch them. By the time someone notices a strange flash or glow, it's often already gone. In recent years, with better technology, scientists have started to take these mysteries more seriously. There are now dedicated projects that monitor the moon constantly, using sensitive instruments that can spot even the smallest changes in light. Whenever something unusual happens, they try to record it from multiple places at once. This helps rule out other causes, like camera glitches or reflections from Earth's atmosphere. With enough careful observation, they hope to finally collect solid proof of what causes these TLPs. For all our progress in space exploration, the moon still has ways of surprising us. We've sent astronauts to walk on its surface. We've brought back rocks. We've mapped its mountains and valleys. And yet, these fleeting, unexplained events remind us that even our nearest neighbor still hides some of its secrets. Interstellar alchemy. The transformation of matter in extreme environments. Matter seems to follow the same familiar rules. Hydrogen drifts peacefully through space. Dust gathers slowly into clumps. Light moves along its steady path. But there are corners of the cosmos where things are anything but calm. There, in the most extreme environments, ordinary matter is pushed beyond its limits. Crushed, heated, torn apart, and rebuilt, the very building blocks of the universe are transformed into something entirely new. This is where cosmic alchemy takes place, a slow, violent, and ongoing process that constantly reshapes the elements themselves. When matter falls toward a black hole, it doesn't simply vanish right away. Before it crosses the event horizon, the point beyond which nothing can escape, it often gets trapped in a swirling disk of gas and dust called an accretion disk. In this disk, particles crash into each other at incredibly high speeds. Friction heats the material until it becomes hotter than almost anything else in the universe. Temperatures soar into the millions of degrees, and the forces at play are so strong that atoms themselves can be stripped apart. Electrons are ripped from their nuclei, leaving behind a soup of charged particles. In this environment, the normal structures of matter break down, and what's left is a cloud of pure energy and particles in constant motion. Inside these disks, heavier elements can form through collisions between particles. New atomic nuclei can fuse together in ways that wouldn't happen under more peaceful conditions. As some of this material spirals outward instead of falling in, it carries these new elements with it, spraying them into the surrounding galaxy. In a sense, black holes don't just consume matter, they also play a part in creating new, complex forms of it. Another place where matter is dramatically changed is inside the remnants of supernova explosions. When a massive star reaches the end of its life, it can explode with such force that the inner core collapses while the outer layers are blasted into space. During the explosion itself, the temperatures and pressures rise so high that elements are forged in mere seconds. Lighter elements like carbon and oxygen are smashed together into heavier ones like gold, uranium, and platinum. These precious metals, which we often think of as rare and valuable on Earth, are born in the heart of dying stars during just these few moments of chaos. The shock wave from the blast moves through space, slamming into nearby clouds of gas and dust. These clouds are compressed and heated by the passing wave, triggering even more changes. Molecules are broken apart. New ones form in their place. Simple gases can turn into complex organic molecules, the very same kinds of molecules that might someday serve as the seeds of life. In this way, the violent death of a star becomes a source of new chemistry that can spread across a galaxy. Near neutron stars, what's left behind after certain types of supernova explosions, magnetic fields can be trillions of times stronger than anything we experience on Earth. These magnetic forces twist and pull on particles, forcing them into narrow beams of radiation or locking them into tight spirals. Inside the crust of a neutron star, the pressure is so intense that regular atoms cannot exist. Electrons are forced into protons, turning them into neutrons. What remains is matter that is so dense that a single teaspoon of it would weigh more than a mountain. This ultra-dense, neutron-rich material may be stable inside the star, but if pieces of it were somehow removed, they would fall apart instantly. It's a form of matter that only survives under the most crushing of conditions. Cosmic rays are high-energy particles that zip through space, often born from the leftovers of supernovae or from the areas around black holes. When these particles hit atoms in interstellar space, they can knock electrons loose or break the atoms into pieces entirely. Over time, this can lead to the creation of rare isotopes, versions of elements with unusual numbers of neutrons. By studying these isotopes in cosmic dust or in the atmospheres of planets, scientists can trace the paths of cosmic rays and see how they've been reshaping matter as they travel across the galaxy. In some regions, the results of all this cosmic alchemy become visible. Glowing clouds called nebulae are filled with the products of past explosions. The colors of these clouds, reds from hydrogen, greens from oxygen, blues from sulfur, tell the story of elements that were made, destroyed, and remade over billions of years. These are the leftovers of stars that once lived and died. Now they wait quietly, drifting through space, until gravity pulls them together again to form new stars and planets. Through all of this, the universe keeps recycling its ingredients. What starts as hydrogen might eventually become iron inside a star. After a supernova, that iron might be scattered into space, only to be pulled into the heart of another forming star. Over time, that star might burn its fuel, die, and add its own batch of new elements to the mix. The process repeats endlessly, with each generation of stars adding more complexity to the universe's chemical recipe. Compact giants. The curious world of ultra-compact dwarf galaxies. Galaxies come in all shapes and sizes. Some stretch across hundreds of thousands of light-years, filled with billions of stars. Others are so faint and small that they barely stand out against the darkness of space. But among these countless galaxies, there is a rare and strange kind that stands apart from the rest. These are the ultra-compact dwarf galaxies, and despite their tiny size, they are some of the most crowded places in the universe. At first glance, an ultra-compact dwarf galaxy doesn't seem like much. They are small, sometimes just a few hundred light-years across. To give that some perspective, our own galaxy, the Milky Way, is over 100,000 light-years wide. That means you could fit an ultra-compact dwarf galaxy into our Milky Way thousands of times over. But while their size is small, their weight tells a very different story. Packed into these tiny spaces are tens of millions of stars, all squeezed tightly together. Some of these galaxies have more mass than entire regions of much larger galaxies, all within a fraction of the space. For a long time, No one even realized these galaxies existed. They are not easy to spot. Their light is faint, and because they are so compact, they can look like single stars or small star clusters through a telescope. It wasn't until the late 1990s that astronomers studying the area around a large galaxy cluster called Fornax noticed something unusual. Objects they thought were just bright star clusters turned out to be entire galaxies, just incredibly small ones. Normally, galaxies form from clouds of gas and dust that slowly come together, creating stars and gathering mass over billions of years. But ultra-compact dwarfs don't seem to follow those same rules. Some scientists believe they are the leftover cores of much larger galaxies that were torn apart long ago. Imagine a large galaxy drifting too close to a bigger one. The larger galaxy's gravity pulls on it, stripping away its outer stars and gas. What's left behind is the dense, heavy center, a compact nugget of stars that used to be the heart of a much bigger system. Over time, this core becomes what we now call an ultra-compact dwarf galaxy. Other scientists think that some ultra-compact dwarfs might have formed on their own, directly from dense clouds of gas that collapsed in the early universe. In this idea, they are like small, heavy versions of regular galaxies that just never grew much larger. Instead of getting pulled apart, they stayed compact from the very beginning, forming stars quickly and holding onto their mass tightly. If you were standing on a planet inside an ultra-compact dwarf galaxy, the night sky would look completely different. Instead of a few thousand stars visible to the naked eye, you might see millions. The sky would shine with constant light from nearby stars, glowing all around you, never going fully dark. Ultra-compact dwarfs also seem to hold clues about dark matter. Dark matter is the invisible material that makes up most of the mass in the universe, though we still don't know exactly what it is. In regular galaxies, dark matter helps hold everything together with its gravity. But in ultra-compact dwarfs, there's something strange going on. Some of them seem to have far more mass than their stars alone can explain, hinting that they might contain large amounts of dark matter too. But in other cases, the amount of dark matter appears surprisingly low. It's a puzzle scientists are still trying to solve. Why would some of these galaxies be full of dark matter, while others seem to have almost none? Could the answer lie in how they formed, or did something happen to strip the dark matter away? These questions can help us figure out the bigger picture of how galaxies grow, change, and survive in the crowded neighborhoods of the universe. Ultra-compact dwarfs are often found near huge galaxy clusters, places where dozens or even hundreds of galaxies gather together. In these crowded regions, galaxies interact all the time, pulling on each other with gravity, exchanging gas, and sometimes even crashing together. It's in places like these that ultra-compact dwarfs seem to thrive, possibly because these environments are perfect for creating the kinds of conditions that break larger galaxies apart and leave behind their dense cores. As telescopes have improved, scientists have started finding more of these compact galaxies, not just in the Fornax cluster, but all over the nearby universe. For something once thought to be rare and unusual, ultra-compact dwarfs may turn out to be surprisingly common in certain parts of the cosmos. But even with more examples to study, they remain some of the most curious and difficult objects to explain. Flash in the sky. Fast blue optical transients, FBOTs, explored. Fast blue optical transients, or FBOTs, are sudden, powerful flashes of blue light that appear in the night sky without warning. They last only a short time, but in those moments they release enormous amounts of energy. In a universe filled with unusual things, FBOTs have quickly become one of the biggest mysteries. The first clue that something unusual was happening came in 2018. That's when astronomers spotted an unexpected burst of light from a galaxy nearly 200 million light-years away. At first, it looked like it might be a supernova. But supernovae are common enough that scientists know how they usually behave. This new event wasn't like a typical supernova at all. It was much brighter. It happened much faster. And the light it gave off had a clear blue color, which made it stand out even more. Because of how strange it was, scientists gave it a name as strange as its sudden nature, the cow. That might sound like an odd name, but it came from the letters in its official name, which just happened to spell cow. In the years since, more of these flashes have been spotted, and each one seems just as strange as the first. FBOTs are hard to catch. They rise quickly, sometimes reaching their peak brightness in just a few days. Then they fade away, leaving almost nothing behind. Unlike supernovae, which can stay visible for weeks or even months, FBOTs don't give much time for scientists to study them. The light from these events is not only fast and bright, but it also leans heavily toward the blue part of the spectrum. That tells scientists that the material involved in the explosion is incredibly hot, hotter than what is seen in most supernovae. But knowing that the material is hot doesn't answer the bigger question: what is causing these flashes in the first place? Several ideas have been suggested, but none of them completely explain what is going on. One of the most popular ideas is that FBOTs are the result of a star being ripped apart by a black hole. When a star drifts too close to a black hole, the black hole's gravity pulls harder on the side of the star that's closest, stretching it out and tearing it into pieces. This process is called a tidal disruption event. As the pieces of the star swirl around and fall into the black hole, they heat up and shine brightly. It seems like a good match for something fast and energetic. But FBOTs happen even faster than most tidal disruption events, and their light has some unusual features that don't quite fit. For example, FBOTs produce stronger radio waves than typical star-shredding events, and they don't fade the same way. It's possible that the black hole idea is part of the answer, but it might not be the whole story. Another idea is that FBOTs are an unusual kind of supernova, maybe caused by a star that was already surrounded by a thick shell of gas before it exploded. In this case, the explosion would slam into that gas, heating it up and creating an extra bright flash of light. This could help explain why FBOTs are so powerful and why they happen so fast. The extra material around the star would give the explosion something to crash into, speeding things up and making the whole event hotter and brighter. But even this idea doesn't explain everything. FBOTs are so rare and so extreme that scientists are starting to wonder if something entirely new is happening. Some researchers think FBOTs might involve objects like neutron stars or black holes forming right in the middle of the explosion itself. When certain stars die, their cores collapse into incredibly dense objects. If that happens while the outer parts of the star are still falling inward, it could lead to an explosion that is much faster and brighter than normal. The newly formed object, whether it's a black hole or a spinning neutron star, could then blast energy back out into the surrounding material, giving the explosion an extra boost. Some scientists call this a central engine model, because the neutron star or black hole at the center is acting like an engine, driving the explosion forward. This might help explain why FBOTs seem to release so much energy in such a short time. It's almost as if something is powering the explosion from within, keeping it going longer and brighter than it otherwise would. Sometimes when black holes or neutron stars form, they shoot out narrow, high-speed jets of material, blasting through space at nearly the speed of light. These jets can punch through the outer layers of a star and escape into the space beyond. If one of these jets happens to be aimed toward Earth, we might see a short, bright flash. This kind of jet-powered explosion has been seen before in events called gamma-ray bursts. FBOTs might be a related type of event, but with differences in how the jets form or what they run into. Maybe the jets in FBOTs don't make gamma rays, but instead heat up material in a way that gives off visible blue light. Many of them have been found in the outer parts of galaxies, far from the busy, crowded areas where stars usually form and die. Most supernovae happen in the parts of galaxies that are filled with young, massive stars. But FBOTs often seem to appear out on the edges in quieter regions where not much else is happening. Why would such powerful events happen in places where there shouldn't be many big stars? Are we missing something about these quiet parts of galaxies? Or are FBOTs coming from an entirely different kind of process? They are so rare that only a handful have ever been seen, and because they appear and disappear so quickly, it's hard to study them in real time. But we are getting better at spotting these brief flashes. Astronomers are using wide-field telescopes that scan large parts of the sky every night. These tools help spot FBOTs sooner, giving scientists a better chance to follow them from start to finish. When another FBOT lights up the sky, astronomers will be ready to focus every tool they have on it, hoping to capture more details and figure out what is really going on. Some researchers are also using computer models to simulate what different explosions would look like. By changing the size of the star, the amount of surrounding gas, or the strength of any jets, they can test which conditions match the real events. These models are getting better as more FBOTs are discovered, but even the best simulations still struggle to explain every detail. For example, FBOTs often give off strong radio waves, which suggests there's a lot of material moving at high speeds. But what's driving that motion? Is it a jet? Is it a shock wave from hitting surrounding gas? Or is it something else entirely? Maybe there are several different ways to create a fast blue flash, and what we're seeing is a mix of different processes that all happen to look similar. Until more are found and studied in detail, the true cause of FBOTs will remain open to debate. The vanishing satellites, confronting the missing satellites problem. Scientists expect to find many small galaxies orbiting larger ones. These smaller galaxies, called satellite galaxies, are like tiny companions that circle around their bigger neighbors. Our best computer models of how galaxies form predict that there should be hundreds, maybe even thousands of these small galaxies around giant galaxies like our own Milky Way. But when astronomers actually count them, there's a surprising problem. The numbers don't match. In fact, they're off by a lot. Instead of hundreds of satellite galaxies, we see only a few dozen. This strange mismatch has become known as the missing satellites problem, and for years, it has left scientists wondering where all the missing galaxies have gone. The problem first showed up when researchers started using computer simulations to test how the universe grew after the Big Bang. These simulations follow the behavior of dark matter. Dark matter helps build the skeletons of galaxies. As these simulations ran, they showed that dark matter should clump together into many small groups. These groups, called halos, would become the homes of satellite galaxies. If the models are correct, every large galaxy, like the Milky Way or the Andromeda galaxy, should be surrounded by a whole swarm of smaller galaxies. But when telescopes scanned the skies, those swarms just weren't there. This problem wasn't small either. The models were predicting 10 times more satellites than we actually saw. For something as carefully designed as a computer simulation of the whole universe, that's a pretty big mistake. It forced scientists to ask hard questions. Where had the models gone so wrong? Were we missing something important about how galaxies form? One idea is that the satellites are actually there, but they're so faint that our telescopes just can't find them. Many of these predicted satellite galaxies would be made up of only a few stars spread over a large area. That means they wouldn't shine very brightly. They'd be like a handful of fireflies scattered across a dark field. If you're standing far away, you might only notice the brightest ones. The others would be too faint to spot. Over the last couple of decades, better telescopes and deeper sky surveys have started to discover more of these tiny, dim galaxies, especially around the Milky Way. But even with these new discoveries, the total number of satellites we see still falls far short of the predictions. Another idea is that not all dark matter halos manage to form galaxies. Just because a patch of dark matter exists doesn't mean it always pulls in enough normal matter, like gas, to make stars. Something might stop that process. For example, when the universe was young, it was filled with high-energy radiation that could heat up gas and stop it from settling into small halos. Without that gas, there would be nothing to form new stars. The dark matter halo would still be there, but it would remain invisible, an empty shell of gravity with no light. In this case, the missing satellites aren't really missing. They're just dark and empty, floating unseen around larger galaxies. Scientists also wonder if some of these small galaxies may have been torn apart. Galaxies pull on each other with their gravity, and when a tiny galaxy gets too close to a much bigger one, the forces can rip it apart. Over billions of years, these shredded satellites could leave behind trails of stars called stellar streams stretched out across the sky. Astronomers have found a few of these streams around the Milky Way, and they are signs that satellite galaxies have been destroyed in the past. If enough satellites were pulled apart this way, that could help explain why we see fewer of them today. The missing galaxies might not have vanished, they might just be scattered. It's possible that our models of dark matter itself might be off. The standard view of dark matter is that it's cold, meaning the particles move slowly and clump together easily. This makes lots of small structures form, which leads to lots of satellite galaxies. But what if dark matter is warm instead? Warm dark matter would move a bit faster and would smooth out the smallest structures, stopping so many small galaxies from forming in the first place. In that case, the models wouldn't predict hundreds of satellites anymore. They would match the lower numbers we actually see. This would mean that the missing satellites problem isn't really a problem at all. Just a clue that dark matter behaves differently than we thought. Small galaxies have a harder time holding on to gas. When big explosions happen inside them, like supernovae, they can blow the gas right out of the galaxy. Without that gas, they can't make new stars, and they stay dark and quiet. If this happened early in the universe's history, many small galaxies might have started out strong but quickly burned out, leaving behind only faint leftovers that are nearly impossible to detect now. And so the search goes on. Surveys are looking deeper into the faintest corners of space, hoping to catch sight of those elusive satellites. Maybe the missing satellites are hiding, or maybe they were never there in the first place. Either way, the mystery of the missing galaxies keeps scientists looking up, waiting for the next clue to appear. When speed defies limits, unraveling superluminal motion. According to everything we know about physics, nothing can move faster than light. Light is supposed to be the fastest thing in the universe. It sets the speed limit that nothing can pass. And yet, when we look closely at certain parts of the sky, we see objects that seem to be racing across the cosmos faster than light. This strange effect is called superluminal motion. Superluminal motion was first noticed when scientists started studying distant galaxies. In the hearts of some of these galaxies are supermassive black holes. These black holes are millions or even billions of times heavier than our Sun. They pull in gas and dust from their surroundings, and as this material falls toward the black hole, it heats up and shines brightly. But not all of that material falls straight in. Some of it gets blasted outward in narrow, powerful jets that shoot out from the black hole's poles. These jets can travel huge distances, stretching far beyond the galaxy itself. When we point our telescopes at these jets, we can track how fast they seem to move, and that's where the mystery begins. In some of these jets, the material appears to move across the sky at several times the speed of light. But scientists quickly realize that what we're seeing is not exactly what it seems. These objects aren't actually breaking the speed limit of the universe. Instead, what we're witnessing is a trick of perspective, a cosmic illusion caused by the way light and motion work together when objects move almost as fast as light itself. To understand this, picture a jet of material shooting out from a black hole. If this jet is pointed nearly straight at us, and if it's moving very close to the speed of light, something strange happens. As the material moves forward, it sends out light along the way. But because the material is moving almost as fast as the light it releases, the later parts of the jet's motion are catching up with the light from the earlier parts. The result is that from our point of view on Earth, the whole jet appears to be moving across the sky much faster than it really is. It's a bit like watching a race where the runner is almost as fast as the sound of the starter's gun. The normal rules of timing start to feel different when speeds get that high. This means that superluminal motion doesn't actually break the laws of physics. The jets aren't really moving faster than light through space. They only look that way because of how their speed, angle, and distance work together. Still, even though it's an illusion, it's one that helps scientists understand just how extreme these jets are. For the effect to appear at all, the jets have to be traveling at speeds very close to light's maximum. That alone tells us we are looking at some of the most energetic and powerful processes in the universe. These cosmic jets come from objects called quasars and blazars. Quasars are distant galaxies with supermassive black holes that are actively feeding on material. Blazars are similar, but with jets that are pointed almost directly at us, which makes the light from the jets much brighter and more noticeable. In both cases, the material in the jets is moving with incredible energy, powered by the intense forces around the black hole. As the material is pushed outward, magnetic fields help shape and direct the jets, keeping them narrow and focused even as they stretch across space. While most of the superluminal motion we've observed comes from these powerful jets, the same basic effect can happen anywhere. Something moves nearly as fast as light and is aimed just right. Studying superluminal motion helps scientists in several ways. For one, it gives clues about the black holes at the centers of these galaxies. By watching how the jets behave over time, astronomers can figure out how much energy is being released and how fast the black hole is spinning. It also helps them learn more about the environments around these black holes, where gravity, heat, and magnetic fields are all working together to create these jets. Tracking these fast-moving objects over years or even decades lets scientists measure changes in the jets, like bends, twists, or fading light. These small changes can reveal what's happening inside the jet, like how clumps of gas move through it, or how shock waves might form as different parts of the jet collide. One of the most famous examples of superluminal motion is found in the galaxy known as M87. This galaxy, which is about 55 million light-years away, has a massive black hole at its center. In 2019, this was the first black hole ever photographed, and its powerful jet has been studied for many years. Parts of that jet appear to move faster than light. Closer to home, we've also seen superluminal motion in smaller systems. In our own galaxy, there are objects called microquasars. These are black holes or neutron stars that have much less mass than the ones in distant galaxies, but they behave in a similar way. They pull in gas from a nearby star, heat it up, and sometimes launch jets. Even though they're much smaller, the jets from microquasars can also show signs of superluminal motion. This shows that the same physics is happening on different scales, from nearby star systems to the far edges of the universe. Cosmic magnetism, the unseen forces shaping galaxies. When we look at pictures of galaxies, we usually notice their bright, swirling arms and glowing centers. These are the features that catch our attention. Stars, dust, and gas make up the shapes we can see. But behind those familiar sights, something invisible is at work. Stretching quietly across the galaxy, unseen forces are shaping the motion of matter. These are magnetic fields. Though we can't see them with our eyes, they thread through the entire universe. They twist and pull on gas clouds, steer charged particles, and even help decide where stars are born. For something so hidden, cosmic magnetism has an enormous influence on the structure and behavior of galaxies. We know that magnets stick to our refrigerators and that compasses point north. This is because of Earth's magnetic field, which is generated deep within the planet's core. But out in space, magnetic fields don't need a planet or a metal core to exist. They are found almost everywhere, stretching through the emptiest parts of the cosmos, running across enormous distances. These cosmic magnetic fields are often weak, much weaker than the field around Earth. But because they reach across such huge areas, they can still control the movement of matter on a grand scale. Scientists believe that the first magnetic fields might have formed not long after the Big Bang. These early fields would have been incredibly small and weak, but over time, as galaxies started to form, those faint fields grew stronger. Moving gas and spinning stars help twist and stretch the magnetic lines, building them up. Today, nearly every galaxy that has been studied seems to have some kind of magnetic field running through it. These fields are often shaped by the galaxy itself, wrapping around its spiral arms or flowing out from its center. Galaxies are full of gas, which is the raw material for making stars. But gas doesn't just sit still in space. It moves and flows, pulled by gravity and pushed by explosions from dying stars. When gas moves through a magnetic field, the field can guide its motion. It acts like invisible rails, steering the gas along certain paths. In some areas, the field might slow the gas down, keeping it from collapsing into new stars. In other places, it might help gather gas together, making it easier for stars to form. In this way, magnetic fields can shape where and when stars are born within a galaxy. When supernova shock waves pass through the magnetic field of a galaxy, they twist and stretch it even more. This adds energy to the field and can create complex patterns. These strong, tangled magnetic areas can then help push particles to incredible speeds, creating cosmic rays that shoot across the galaxy and even reach Earth. Magnetic fields are believed to play a key role in forming and aiming the charged particle jets of supermassive black holes. Without magnetic forces twisting around the black hole, the jets might never form. These jets can stretch for thousands of light years. Since they are invisible, scientists have to explore them indirectly. One way is by studying the light that comes from distant galaxies. As this light passes through magnetic fields, its waves can twist slightly, a process called polarization. By measuring these twists, scientists can figure out the direction and strength of the magnetic fields the light has passed through. Radio telescopes are especially useful for this. They can detect the faint signals that carry the fingerprints of magnetism across the universe. Scientists are still trying to figure out how magnetic fields first formed, how they grow, and how they interact with other forces in the universe. Some theories suggest that tiny differences in the early universe created the seeds of magnetic fields. Others think that turbulence, chaotic movement of gas, plays a major role in amplifying these fields over time. It's likely that both ideas are part of the story, but pinning down the exact process is difficult, and research is ongoing. Every time gas moves, stars form, or galaxies collide, magnetic fields are involved. They are woven into the very fabric of space. And while we may not see them, their effects are everywhere. With better data, we may finally get a clearer picture of how these hidden forces operate. Piece by piece, the invisible structure of the universe is becoming visible, and magnetic fields are a big part of that story. The more we learn about them, the better we understand not just how galaxies look, but why they behave the way they do. Cosmic strings and the fabric of reality. Imagine the universe as an enormous, stretched-out piece of fabric. It's not made of cloth, of course, but it's a helpful way to picture the vast, invisible field we all live in called space-time. This fabric bends and twists whenever something with mass, like a star or planet, rests on it. But some scientists believe there might be more to this fabric than just gentle curves and dips. They think the early universe may have left behind tiny, incredibly thin threads woven into the fabric itself. These are called cosmic strings. Cosmic strings are not strings in the usual sense. You wouldn't be able to tie them into a bow or wind them into a ball. They are thought to be unimaginably thin, so narrow that they make a single atom seem like a giant balloon. But despite their thinness, they could be incredibly heavy. Just a small piece of a cosmic string might weigh as much as a mountain. These strings would stretch across huge distances, possibly even across the entire universe. If they exist, they would be among the oldest things in the cosmos, formed moments after the Big Bang when the universe was still extremely hot and dense. The idea of cosmic strings comes from studying how the universe cooled down after the Big Bang. Back then, everything was in a state of chaos. Temperatures were so high that all the forces of nature were mixed together. As things cooled, these forces separated, sort of like how ice forms in water as it gets cold enough. But just as ice can form cracks as it freezes, the universe might have developed its own cracks when it cooled. Scientists think cosmic strings are like these cracks, leftover scars from the earliest moments of existence. These strings wouldn't look like cracks to us, though. If we could see them, they'd appear as invisible thread-like objects cutting through space. They might pull on everything around them through gravity. A cosmic string passing through our solar system could bend the light of distant stars, creating strange visual effects. Light would bend around the string, making it seem like one star has turned into two. This is called gravitational lensing, and it's one way astronomers have tried to look for cosmic strings in the night sky. So far, no one has found clear evidence of a cosmic string, but that hasn't stopped researchers from looking. The universe is huge, and cosmic strings could be very rare. If they stretch for billions of light years, the chances of one passing close enough to Earth to study might be small. Still, people are hopeful. What makes cosmic strings so interesting isn't just the thought of them slicing through the cosmos, it's what they might tell us about our reality. If cosmic strings are real, they could be proof that the universe has a deeper, hidden structure. They might connect the small, invisible world of particles with the giant, sprawling world of galaxies and stars. In other words, they could be a bridge between the tiniest and largest parts of existence. Some researchers think cosmic strings might even help explain dark matter and dark energy, two of the biggest mysteries in science. Dark energy is the force pushing the universe to expand faster and faster. If cosmic strings exist, they might interact with these strange substances, or even help create them. Cosmic strings might also produce waves in space-time called gravitational waves, which ripple through the universe whenever something really massive moves around. When scientists first detected gravitational waves in 2015, they were picking up signals from colliding black holes. But cosmic strings could make gravitational waves as well. If two pieces of a string crossed paths, they might snap or loop together, sending out bursts of gravitational waves. Some researchers are now checking gravitational wave data, looking for signals that might come from strings rather than black holes or neutron stars. If we were somehow able to get close to a cosmic string, it would be an odd experience. You wouldn't see it or touch it like a regular object, but its gravity would affect everything nearby. Time might move differently around it. Distances might stretch or shrink. Traveling along a cosmic string could, in theory, allow for shortcuts through space. It's been suggested that a pair of cosmic strings might even create something like a wormhole, a tunnel through space-time that could let you move from one place in the universe to another much faster than light could travel. Cosmic strings touch on the Big Bang, gravity, particles, energy, and the very shape of the universe. They even give us new ways to think about time and space, and yet they remain completely hypothetical. We don't know if they exist. We may never know. But searching for them pushes us to ask deeper questions about where we came from and what the universe is made of. It's strange to think that something so small and thin could stretch across billions of light years and influence the motion of galaxies. But that's the kind of place the universe is. The more we learn, the more we realize that it's built on ideas that seem impossible. Elemental puzzles. The cosmological lithium problem. Lithium is something many people know because of the small batteries we use every day. But in space, lithium is part of a much bigger story. It's one of the first elements created right after the Big Bang, and it's tied to the very beginning of everything. Still, when astronomers look at the universe today, they find far less lithium than they should. This is called the cosmological lithium problem, and it has been confusing scientists for decades. To understand why this is such a puzzle, it helps to go back to the very start. About 13.8 billion years ago, the Big Bang happened. In the minutes that followed, the first atoms began to form. During this time, called Big Bang nucleosynthesis, the universe made large amounts of hydrogen and helium. A tiny bit of lithium was created too. Scientists can figure out how much of each element should have formed by using simple physics. These predictions match what we see when it comes to hydrogen and helium. But lithium doesn't fit the pattern. When we measure the oldest stars, the ones that have been around since the early days of the universe, they contain only about a third of the lithium we expect. This mismatch is the heart of the lithium problem. It might seem like a small thing. Why worry if there's less lithium than expected? But the truth is, this matters because the early universe followed rules. If our predictions match for hydrogen and helium but fall apart with lithium, it means something about those rules might be missing. The formulas scientists use to describe the early moments of the universe depend on understanding how the first elements formed. If lithium doesn't behave as predicted, then either something strange happened to it later, or something about the early universe isn't quite what we thought. Astronomers have worked hard to figure out what might have gone wrong. One idea is that the lithium was made in the right amounts during the Big Bang, but something destroyed it afterward. Maybe the first stars, which were bigger and hotter than stars today, burned through their lithium and mixed it into their insides where it couldn't be seen anymore. These early stars may have been much more violent than we imagine, pulling elements down into their cores where they were broken apart by extreme heat. Over billions of years, the lithium that survived could have been hidden deep inside these stars or spread out too thinly to find. Another thought is that the stars we measure now weren't the first ones to hold lithium. Over time, stars are born and die, and they recycle material into the next generation of stars. Maybe the lithium we see today isn't from the Big Bang at all, but came from later events like cosmic rays smashing into other atoms, making fresh lithium. This would mean the original lithium is mostly gone and we're only seeing the leftovers from other later processes. But when astronomers look at very old stars, the same low levels of lithium show up again and again. These stars are in different places, from our own galaxy to others nearby, and yet the lithium amounts are always too low. If destruction by stars was the reason, we'd expect some variety in the numbers. But that's not what we see. The consistency makes the puzzle even deeper. Maybe there was something happening during the first few minutes of the universe that we don't understand yet. Some scientists have wondered if unknown particles or forces were at play during Big Bang nucleosynthesis. If new types of particles were interacting with the lithium, they might have changed how much was created. These particles could be part of dark matter. If dark matter played a part in shaping the early elements, it could explain why lithium ended up being so rare. Other theories suggest that there might have been small changes in the values of physical constants long ago. The universe is built on a set of numbers that control how things like gravity and nuclear reactions work. If those numbers were slightly different during the Big Bang, even just by a little, the amount of lithium created could change. So far, there's no strong evidence for this, but it's an idea that some scientists keep exploring. There have even been experiments here on Earth to try to figure it out. In labs, scientists create conditions like those that existed just after the Big Bang. They smash particles together to recreate the reactions that made the first elements. These tests have helped confirm the predictions for hydrogen and helium, but lithium still doesn't quite add up. It's as if the answer is always just out of reach. The early universe set the stage for everything we see today. Galaxies, stars, planets, and even life all grew out of those first few moments. If there's something wrong with our understanding of what happened back then, it could mean our picture of the entire universe is missing a key piece. For now, the lithium problem remains unsolved. Astronomers keep looking for new clues. They search for old stars in untouched parts of the galaxy. They build better models of how stars form and evolve. Each of these steps might get us closer to understanding why the universe made less lithium than it should have. Rewriting cosmic chemistry. Rethinking Big Bang nucleosynthesis. The standard model of Big Bang nucleosynthesis is based on clear, simple physics. The universe was extremely hot and dense. As it expanded and cooled, protons and neutrons combined to form nuclei. In just a few minutes, the basic elements were created. After that, things settled down. At least that's what the model says. But certain things don't quite add up. Lithium is the most famous problem. But that might only be part of the picture. Other small differences have popped up, little clues that the chemistry of the early universe may not have been as straightforward as we once thought. Some wonder if the early universe might have had different conditions than we expected. Maybe the temperature dropped faster or slower than we thought. Maybe the density of matter wasn't exactly what we predicted. Even small changes in these factors could affect how the elements formed. With just a slight difference in the balance of heat and particles, the entire recipe for creating the first elements could shift. Researchers are now carefully testing these possibilities with computer models and experiments. The early universe was full of energy, and it's possible that particles we haven't discovered yet were part of the process. If these particles interacted with protons and neutrons, they might have changed the way elements formed. For example, if there were extra types of neutrinos, they could have carried away energy. This would have affected the speed of reactions and the final amounts of each element. Some scientists call these hypothetical particles sterile neutrinos because they don't seem to do much, but their presence could still change the whole outcome of nucleosynthesis. Some scientists are exploring whether the constants we take for granted today, things like the speed of light or the strength of the strong nuclear force, might not have always been the same. This is a bold idea, but it could provide answers where the standard model cannot. Others are looking beyond the Big Bang itself. Maybe the universe we live in wasn't the first one. There are theories about cosmic cycles, where the universe expands and contracts over and over. In these ideas, traces of previous universes might have affected the next round of element formation. If some leftover particles or energies survived from an earlier universe, they could have added unexpected ingredients to the mix, changing the final balance of elements. In the early universe, matter and antimatter were supposed to exist in equal amounts. But today, matter dominates and antimatter is rare. If there was more antimatter than we thought back then, or if it behaved in unusual ways, it might have changed how elements formed. Collisions between matter and antimatter release enormous energy. If these events happened unevenly, they could have left a mark on nucleosynthesis, tweaking the recipe in ways we haven't fully understood yet. Of course, with every new idea, there are challenges. For a theory to work, it has to match what we see in the universe today. It's not enough to explain the lithium problem. The same model also has to get hydrogen and helium right. So far, no alternative theory has fully replaced the standard model, but the search continues. Beyond the observable, unmasking ultra-diffuse galaxies. Some galaxies are easy to spot. Their bright cores shine across the universe. Their swirling arms glow with countless stars. But not all galaxies announce themselves so loudly. Some are quiet, soft, and barely there. These are the ultra-diffuse galaxies. They spread out over vast distances, as wide as our own Milky Way, but they hold far fewer stars. From a distance, they are like faint smudges on the sky. So faint, in fact, that for a long time no one even knew they were there. But now that we've started to find them, these ghostly galaxies are raising big questions about how galaxies form, how they survive, and what invisible forces might be holding them together. When astronomers first started looking at ultra-diffuse galaxies, it was almost by accident. These galaxies are so dim that normal telescopes can easily miss them. They blend into the background of space. It takes very sensitive equipment and long observation times just to pull them into view. But once they began showing up, scientists noticed something strange. These galaxies were huge. They stretched across tens of thousands of light-years, but despite their size, they barely had any stars. It was as if someone had taken a normal galaxy and erased most of the stars, leaving just a thin trace behind. Finding a galaxy with so few stars leads to a natural question. How do they hold together? Stars and gas have mass, and mass creates gravity. In regular galaxies, there's enough matter pulling everything inward to keep the system stable. But ultra-diffuse galaxies have very little visible matter. By all rights, they should be fragile. They should tear apart when they pass near larger galaxies, yet somehow they stay together. This is part of what makes them so fascinating. The fact that they are stable suggests there might be something more going on beneath the surface. One idea is that ultra-diffuse galaxies might have an unusually large amount of dark matter. Maybe these faint galaxies are wrapped in big clouds of dark matter. In some cases, this might be true. A few ultra-diffuse galaxies seem to behave like they are sitting inside very massive halos of dark matter. Their stars move in ways that suggest there's a lot of hidden mass nearby. But then there are others that appear to have almost no dark matter at all. These galaxies are just as faint and just as spread out, but the way their stars move hints that they are barely holding on. It's a puzzle that no one has fully solved. Normal galaxies are thought to form from clouds of gas collapsing under their own gravity. Over time, this gas turns into stars, and the galaxy grows. But if you have a huge galaxy that never built up many stars, something must have slowed that process down. Maybe strong winds from nearby galaxies blew the gas away before it could settle. Maybe supernova explosions pushed the gas out into space before more stars could form. Or maybe these galaxies formed in areas of the universe where there just wasn't much material to work with from the start. Their environments give us some clues. Many ultra-diffuse galaxies have been found in big clusters of galaxies. These are busy neighborhoods, filled with other galaxies moving quickly through space. In these crowded areas, smaller galaxies can get pushed and pulled in different directions. Their gas can be stripped away as they pass through hot clouds of material. This process might leave behind a bare, faint galaxy. But not all ultra-diffuse galaxies live in crowded clusters. Some are found all alone, floating far from their neighbors. In these quieter places, the stripping effect doesn't happen, so something else must have created their dim, spread-out shapes. Part of the challenge is just finding them. Their faintness makes them easy to overlook. Traditional sky surveys, which look for bright spots of light, miss most of these galaxies. It's only with newer, more sensitive telescopes that we've been able to detect them. Surveys designed to look for low surface brightness have turned up hundreds of candidates, and the more we find, the more complex the picture becomes. A few of them seem to have an unusually high number of globular clusters. Globular clusters are dense groups of old stars. They usually orbit around larger galaxies. But here we find them surrounding these faint, barely there galaxies. Why would such dim galaxies have such rich systems of clusters? It's another piece of the mystery. Maybe these galaxies were once something more. Perhaps they started off as regular galaxies and were stripped down over time, leaving just the faint remains. The globular clusters, being more tightly bound, stayed in place while the rest of the galaxy faded. The search for answers is leading astronomers to rethink some old ideas. We used to think of galaxies as falling into neat categories, big or small, bright or faint, spiral or elliptical. But ultra-diffuse galaxies don't fit cleanly into those boxes. They show us that the universe has more variety than we once believed. Galaxies can be enormous without being bright. They can be stable without much visible mass. And they can exist in both busy clusters and quiet, empty parts of space. Stellar relics. The role of fossil structures in cosmic evolution. Scattered across the universe are quiet witnesses to a time long before our own. These are the fossil structures of space, ancient remains left behind from the early days of star formation. They sit silently in the vast darkness, unchanged for billions of years. To most, they might seem like little more than leftover debris, but to scientists, they are like time capsules. Each one carries information about how the first stars formed, how galaxies came together, and how the universe grew from something simple into the complex place we see today. By studying these forgotten pieces, we can trace the story of cosmic evolution, step by step. Fossil structures take many forms. Some are old star clusters. Some are faint galaxies that stopped changing a long time ago. Others are pockets of gas, frozen in time since the first few billion years after the Big Bang. These objects stand apart because while the rest of the universe kept moving forward, they seemed to pause. They no longer formed new stars. They didn't grow or collide with other systems in any major way. They simply remained, quietly drifting through space, carrying the patterns and chemistry of an earlier age. One of the clearest examples of a fossil structure is what's known as an ancient star cluster. These are dense groups of stars that formed all at once long ago. Many of them are nearly as old as the universe itself. When astronomers look at the stars inside these clusters, they can see the same chemical fingerprints across the whole group. This tells us that these stars were born from the same cloud of gas at the same time. And because the gas they came from was still fairly pure, mostly hydrogen and helium with only small traces of heavier elements, it means these clusters formed before generations of stars had a chance to fill the universe with new material. Another example of a fossil structure is found in galaxies that are often called red and dead. These are galaxies that burned brightly billions of years ago, but have long since run out of the gas needed to make new stars. Their stars are old and cool, giving off reddish light. Without fresh gas, these galaxies sit quietly, slowly aging. But their shapes and contents tell us a lot. We can look at how their stars are spread out, how they move, and what they're made of. All of this helps scientists figure out what the conditions were like back when the galaxy was still young and active. In a way, these galaxies hold a frozen record of a much earlier time. There are also even quieter fossil structures, ones made mostly of gas. In some areas of space, clouds of hydrogen and helium have remained untouched for billions of years. These clouds may never have formed many stars at all. They're like leftovers from the early universe, still floating out there, barely disturbed. By studying these clouds, scientists get a rare look at what the universe's raw material looked like before stars and galaxies turned much of it into heavier elements and more complicated structures. Modern galaxies, including our own Milky Way, are built from pieces that formed long ago. Many small galaxies and star clusters merged together to create the larger systems we see now. When astronomers model galaxy formation, they often start with small, simple systems. Over time, gravity pulls these systems together, stacking them up and blending them into something bigger. But by looking at real fossil structures, we can check whether these models match what actually happened. Sometimes fossil structures even survive inside larger galaxies. The Milky Way has several ancient star clusters orbiting its center. These clusters are much older than most of the stars in our galaxy. They probably formed before the Milky Way was even fully assembled. As other, smaller galaxies merged into the Milky Way, some of their fossil structures were pulled in and became part of the larger system. This means that, floating above and below the galaxy's spiral arms, we can find these older relics still moving through the same space as much younger stars. It's like finding pieces of ancient ruins standing among modern buildings, a visible link between very different eras. In some cases, astronomers have even been able to identify fossil galaxies. These are small, faint galaxies that seem to have stopped growing not long after they began. They formed a few stars in the early days of the universe, but then something cut off their supply of gas. Without new gas, star formation stopped, and the galaxies stayed the same. For billions of years, they've drifted through space, barely changing. When we find these galaxies today, their small numbers of old stars give us a direct glimpse of what conditions must have been like when they were young. They provide clues about what the early universe did to small galaxies and how some systems failed to grow while others thrived. We can see the afterglow of the Big Bang. We can observe galaxies forming and colliding today. But the middle parts, the slow, patient assembly of complex structures, are harder to study. Fossil structures act like missing pages from a history book. Each one carries details from a time we can't observe directly. By piecing them together, scientists can build a more complete picture of how the universe unfolded over billions of years. If early star formation had been much faster or much slower, the balance of elements in the universe would be very different. If galaxies had merged in different ways or at different times, the cosmic web of structure we see today might not have formed. Fossil structures preserve the results of those early decisions. They show us what worked, what lasted, and what didn't. Explosive signatures, unconventional supernovae and their remnants. A massive star reaches the end of its life, runs out of fuel, and collapses under its own weight. That collapse causes a violent explosion, sending out shockwaves and creating a bright light that can outshine entire galaxies. The leftovers form either a neutron star or a black hole, and the surrounding space is filled with glowing gas and dust. This was the classic picture of a supernova. But as telescopes and technology improved, scientists started noticing explosions that didn't follow the usual rules. These strange, unconventional supernovae have become a mystery of their own, offering new questions and surprising clues about how the universe works. One type of unusual supernova is called a pair instability supernova. These happen in extremely massive stars, much larger than most of the ones we see today. When these stars get hot enough, they create pairs of particles made of matter and antimatter. These pairs steal energy from the star's core, weakening the pressure that holds the star up. Without that support, the star collapses and explodes with incredible force. But unlike typical supernovae, which leave something behind, pair instability supernovae tear the entire star apart. Nothing is left. No neutron star, no black hole, just a vast cloud of gas and heavy elements spreading into space. It's complete destruction, and while these events are thought to be rare now, they may have been common in the early universe when stars were much bigger than they are today. Another strange type is the so-called electron capture supernova. These happen in stars that aren't quite massive enough to collapse like the bigger ones, but still end their lives in a powerful way. In these stars, electrons get forced into the atomic nuclei, which makes the core unstable. When that happens, the star falls in on itself, triggering an explosion. What makes these supernovae special is that they sit right on the boundary between normal stars and the huge ones that make traditional supernovae. The explosions are weaker and the remnants are lighter, but they still leave behind neutron stars. These are like quiet middle ground explosions, showing us that there isn't just one path a dying star can take. But not all unconventional supernova are just about how big the star was or what kind of collapse happened. Some are strange because of where they occur or what happens afterward. There are supernovae that happen in binary star systems where two stars are orbiting each other. In these cases, material from one star can flow onto its partner, adding extra weight. When the star getting the extra material becomes too heavy, it explodes. But the blast doesn't just throw debris out into space. Sometimes it slams into the nearby companion star, stripping away part of its outer layers and giving the explosion an odd shape or brightness. These systems can leave behind unique remnants, like fast-moving stars that have been pushed out of their orbits or clouds of gas with strange chemical signatures. Some supernovae seem far too bright for what they should be. These are known as superluminous supernovae. They can shine up to 100 times brighter than a normal supernova, and scientists are still trying to figure out why. One idea is that these explosions are powered by something called a magnetar, which is a type of neutron star with a magnetic field trillions of times stronger than Earth's. As the magnetar spins, it sends out energy that lights up the surrounding gas, making the supernova much brighter and longer-lasting than usual. But not every superluminous supernova seems to fit this idea, and some might involve other strange processes. When a traditional supernova happens, the leftover material forms a supernova remnant, a cloud of gas and dust that expands over time. These remnants glow in different kinds of light, like X-rays and radio waves, and they can last for thousands of years. But the remnants of unconventional supernovae often have strange shapes, odd chemical patterns, or unusual speeds. Some show evidence of elements that shouldn't be there in large amounts. Others have gas moving faster or slower than expected. Some remnants are even missing, possibly because the explosion was so strong that everything was blown too far apart to leave behind a noticeable structure. There are places where scientists see signs of two explosions happening in quick succession. One theory suggests that in some stars, the outer layers might be blown off first in a smaller eruption, only for the core to collapse shortly after and cause the main supernova. This two-step process could explain some of the oddest remnants, where there's a mixture of young and old material moving together in the same cloud. These explosions help shape the galaxies around them. When a supernova goes off, it pushes out heavy elements like iron, gold, and nickel into space. Over time, those elements become part of new stars, planets, and even life itself. Unusual supernovae, with their powerful blasts and strange chemistry, may have added different kinds of elements or spread them out in unexpected ways. This means that the very makeup of the universe we see today may have been influenced by these odd and rare explosions. Astronomers continue to discover new types of supernovae that don't fit any known category. Some are faster than expected, some are dimmer, some seem to switch on and off. Even with all our tools and observations, space is still full of surprises. Cosmic bubbles, structures born from stellar cataclysms. Cosmic bubbles are huge, round cavities carved into the interstellar medium by the powerful forces of dying stars. They are the results of violent events such as supernova and strong stellar winds that push, pull, and reshape the gas and dust floating between the stars. In doing so, they leave behind these enormous hollow structures that drift across space for millions of years. The process begins with a star, often a large one, many times heavier than our Sun. These stars don't just sit quietly in the sky. They are constantly pouring out streams of charged particles at incredible speeds. This flow is called a stellar wind, and over time, it pushes against the gas and dust that fill the spaces between stars. Slowly, steadily, the wind clears out a region around the star, creating a growing cavity. What's left is a shell of gas that has been pushed outward, forming the edges of a bubble. Even before the star dies, its presence begins sculpting its surroundings in ways that can stretch across light years. Many of these same stars eventually run out of fuel and explode as supernovae. When that happens, an even more powerful blast tears through the space around the star, sending shock waves far beyond what the stellar winds alone could accomplish. The material from the explosion slams into the walls of the bubble that the stellar wind had built, making the structure larger, more defined, and much more energetic. This is how some of the largest and most noticeable cosmic bubbles are born. One well-known example of this process is the Bubble Nebula. Located about 7,100 light-years from Earth, this bubble was created by a massive star whose winds have been blowing strong for millions of years. The result is a nearly perfect sphere of gas glowing from the energy of nearby starlight. Inside the bubble, the gas has been cleared away, leaving a mostly empty space, while the outer shell shines where the pushed gas has piled up. It's like looking at the aftermath of a storm that swept through a quiet town, leaving the streets clear and the debris piled up on the edges. When a bubble expands, it moves the gas around it, pushing some of it into dense clumps. In those clumps, gravity can take over and begin the process of forming new stars. So while the death of one star or the fierce winds from another can seem like an end, it often marks the start of something new. Whole generations of stars may owe their existence to the bubbles carved out by their larger, older neighbors. Some cosmic bubbles grow to truly enormous sizes. In our own galaxy, the Milky Way, there are bubbles that stretch for hundreds or even thousands of light years. These aren't formed by just one star, but by the combined efforts of many. In places where clusters of massive stars are packed together, their winds and explosions overlap, joining their bubbles into even larger structures. Over time, these massive cavities can dominate entire regions of a galaxy. They create clearings in the interstellar medium where the normal, smooth spread of gas is interrupted by great voids and shell-like structures. One of the largest examples near our galaxy is known as the local bubble. We are actually inside this bubble right now, floating within its boundaries. Scientists believe it was formed by a series of supernova explosions that happened millions of years ago. As each star exploded, the shock waves expanded the bubble further, pushing gas outward and leaving behind the low-density space we now occupy. Thanks to this, our corner of the galaxy is less crowded with gas than other places. The local bubble continues to shape the paths of stars and the movement of gas clouds nearby, silently influencing the future of our own solar system. In other galaxies, we can spot the glowing shells of gas surrounding young, massive star clusters. Some galaxies even seem to be filled with overlapping bubbles, with their shapes traced out by the light of ionized gas. These places tell the same story over and over. Stars are not just tiny points of light. They are powerful engines that change the space around them in lasting and visible ways. But not every bubble is smooth and round. The environments in which they form are often uneven. Gas clouds might be thicker on one side or stretched into long filaments. When the winds or shock waves hit these different areas, the bubbles can become distorted, growing into strange shapes that reflect the chaotic nature of space. Some bubbles open up on one end, spilling material out into the galaxy like smoke drifting from a chimney. Others develop ripples and waves along their edges, marking where the force of the expanding shell has met resistance or run into new material. We can watch them grow, frame by frame, with telescopes that see in different kinds of light. X-ray telescopes reveal the hot, energetic centers of the bubbles. Radio telescopes trace the outlines of the cooler gas that makes up the shell. Optical telescopes capture the glow of the ionized gas lit up by the ultraviolet light from nearby stars. Together, these views give us a full picture of how these structures come to be, how they live, and eventually how they fade. Beyond the standard model, hints of new physics in cosmic anomalies. The universe follows rules, and scientists have spent centuries working out the patterns of nature, from the smallest particles to the largest galaxies. These rules are written into what is known as the Standard Model of Physics. It's a detailed guide to how the most basic parts of matter behave and how the forces of nature interact. For decades, the Standard Model has been able to explain almost everything we can see, measure, and test. But there are signs that it might not tell the whole story. Out there in space, certain strange observations have started to appear. These cosmic anomalies don't quite fit within the framework of the Standard Model. One of the clearest hints comes from dark matter. The Standard Model doesn't include dark matter. It doesn't explain what it is, what it's made of, or why it's there. This gap in our understanding leaves a wide-open space for new physics to step in and provide answers. Maybe dark matter is made of particles we haven't discovered yet. Or maybe the problem goes even deeper. Maybe the way we understand gravity itself is incomplete. Then there's the case of dark energy. While dark matter holds things together, dark energy seems to push things apart. When astronomers observed distant galaxies in the late 1990s, they found that the universe's expansion was speeding up. This was unexpected. According to the Standard Model, gravity should slowly pull everything back together over time. Instead, something is causing the universe to expand faster and faster. Scientists call this force dark energy, but beyond the name, very little is understood about it. It doesn't behave like anything else we know. It acts like an invisible pressure-filling space, and its presence hints that there are parts of the universe's story that our current physics can't yet explain. Another mystery comes from the CMB. When scientists map this faint glow across the sky, they expect to see a smooth, even pattern with small, random bumps. But there are unexpected alignments and cold spots that shouldn't be there. One part of the sky, known as the axis of evil, shows an unusual pattern that doesn't match the random noise predicted by the Standard Model. No one is sure what it means. It could be a coincidence, or it could be a clue that something about the early universe worked differently than we think. Even neutrinos have raised questions. The Standard Model predicts certain properties for neutrinos, including their mass. For a long time, neutrinos were believed to be massless, but experiments showed that they do have a small mass after all. This discovery already pushed the standard model to its limits. Now, hints from space suggest there might be more types of neutrinos than we currently know. Fast radio bursts are brief, powerful flashes of radio waves coming from distant galaxies that last only milliseconds but release as much energy as the sun does in days. Scientists still don't know what causes them. Some think they might come from the magnetic fields of neutron stars. Others suggest collisions between dense objects like black holes or the collapse of massive stars. But the exact cause remains a mystery. And the sheer energy involved raises questions about what kind of forces are at play in these distant parts of the universe. If these bursts turn out to involve processes that don't match current theories, they could offer yet another doorway into new physics. Cosmic rays race through space at nearly the speed of light, hitting Earth's atmosphere from every direction. Most of them come from well-known sources like the sun or distant supernovae. But some cosmic rays have been measured with energies far beyond what our theories predict. It's like finding a car driving faster than the laws of physics allow. Scientists are still trying to figure out where these ultra-high-energy cosmic rays come from and how they gain so much power. Over time, these small cracks in the foundation of modern physics have become harder to ignore. Each strange observation adds a piece to a growing puzzle. On their own, they might be easy to write off as rare events or measurement errors. But together, they suggest that something larger might be going on. Maybe the universe is working under rules that we haven't even begun to uncover. In a way, the universe is like a giant laboratory, running experiments on a scale that we could never recreate here on Earth. Every supernova, every black hole, every distant burst of light carries data from the frontier of physics. By watching closely, collecting the signals, and piecing them together, scientists hope to unlock the next chapter of understanding. Unsettling paradoxes, when observations defy conventional theories. Sometimes the universe doesn't seem to follow its own rules. Scientists spend years building models to explain how things should work in space. They test these models with careful math and computer simulations. They check their ideas with telescopes and satellites, but every now and then, something happens out there that doesn't fit. These strange cases where reality doesn't match what theory says are known as paradoxes. They are like warning signs telling us that there might be gaps in what we thought was settled science. One of the best-known paradoxes in astronomy is called the missing baryon problem. In simple terms, scientists know how much normal matter, the kind that makes up stars, planets, and people, should have been created during the early days of the universe. This matter is made of particles called baryons. By measuring the leftover light from the Big Bang and studying the oldest gases, they can predict how many baryons should exist. But when they count up all the normal matter in galaxies, stars, and gas clouds today, they find only about half of what should be there. Over time, astronomers have found some of this missing matter hiding in hot gas between galaxies. But not all of it. The search continues, and no one is sure if we just haven't looked in the right places or if something bigger is going on. Another puzzle is called the cooling flow problem. In the centers of large galaxy clusters, there is a lot of super-hot gas. This gas is so hot that it should cool down over time and fall toward the middle of the cluster. There, it should form new stars as it condenses. But when scientists look, they don't see nearly as much cool gas or as many new stars as the models predict. The gas stays hotter for much longer than expected. Something is stopping the cooling process, but it's not clear what. One idea is that giant black holes in the middle of these clusters are blasting out energy, keeping the gas hot. But even that doesn't fully explain the missing cooling flows. It's a case where observation and theory are not in agreement, leaving a gap in our understanding. There's also the cusp core problem. When astronomers model how dark matter gathers inside galaxies, their simulations predict that dark matter should be most crowded at the center. These centers, or cusps, should show a sharp peak in density, but when they measure real galaxies, especially small ones, they often find flatter centers, more like cores than cusps. The dark matter seems to spread out more evenly than it should. This doesn't match what computer models say should happen. Scientists have tried to adjust their theories. Maybe the stars or gas push the dark matter outward somehow. Maybe dark matter has unexpected properties. But so far, there's no simple solution that works for every galaxy. Then there's the Hubble tension. The Hubble constant is a number that tells us how fast the universe is expanding. You can measure it in different ways. One way is by looking at the light from distant galaxies and watching how quickly they move away. Another way is by studying the leftover glow from the Big Bang and calculating how the universe has expanded since then. But here's the problem. The two methods give different answers, and not just slightly different. The numbers are far enough apart that scientists are starting to think there might be something wrong with the standard model of cosmology itself. Maybe there's a new kind of energy at work. Maybe there are unknown particles affecting the early universe. Or maybe we're missing a key piece of the puzzle entirely. Paradoxes like these keep scientists up at night. They suggest that we may be standing on the edge of new discoveries without even knowing it. These aren't small mistakes or little tweaks that need fixing. They are deep contradictions between what the universe does and what our best ideas say it should do. Each paradox is like a locked door. Behind that door could be a new kind of physics, a better understanding of how the universe works, or a completely unexpected answer we haven't even imagined. As more powerful telescopes and instruments are built, the list of cosmic paradoxes grows. It seems that the deeper we look into space, the more ways we find that reality doesn't quite match the rule book we've written for it. Some of these problems might eventually be solved with better data or new ideas that patch up the old theories, but others might force us to rethink the basics of how we believe the cosmos operates. The edge of the universe, probing cosmic boundaries and beyond. The observable universe is the part of the cosmos we can see, limited by how far light has been able to travel since the beginning of time. It stretches out about 46 billion light-years in every direction. That means from Earth we can see galaxies, stars, and cosmic structures within a sphere that large. But it's important to realize that we're not at the center of the entire universe, just the center of what we can observe. If you were standing on a planet billions of light-years away, your observable universe would look different. Every spot in the universe has its own bubble of what it can see. This boundary isn't something physical like a wall or a fence. It's simply the farthest distance that light has been able to reach us since the universe began about 13.8 billion years ago. Looking out toward the edge of the observable universe means looking back in time. The farther away something is, the older the light we see from it. Some of the light hitting our telescopes today started its journey shortly after the Big Bang. These ancient signals give us clues about how the first galaxies formed, how the first stars lit up, and what the early universe looked like. But as we look closer to that edge, things get faint, stretched out, and harder to understand. The expansion of space itself makes this even more complicated. The universe is growing, and distant galaxies are moving away from us faster and faster. Eventually, some will speed away so fast that their light will never reach us again, no matter how long we wait. So what happens beyond the observable universe? This is where our knowledge starts to thin out. There's no real evidence that the universe just stops at the limits of what we can see. Most scientists think it keeps going. In fact, it might be much larger, possibly infinite. We just don't have a way to observe or measure what's out there. It's like standing in the middle of a foggy field. You can only see as far as the fog allows, but you suspect the field goes on much farther than that. Some scientists have wondered if the universe wraps around itself. In that case, if you traveled far enough in one direction, you might eventually end up back where you started, like walking around the surface of a sphere. This idea is called a finite but unbounded universe. It has no edges, but it's not infinite either. It's one possibility among many, and while it sounds strange, it matches up with some models of space and time, but for now, there's no clear proof that this is the case. If there's more universe beyond what we can see, could there be completely different regions with their own unique properties? Maybe places where the laws of physics work differently, or where matter is arranged in entirely unfamiliar ways. Some theories even suggest the existence of other universes entirely beyond our own. These multiverse ideas come from deep within the mathematics of certain physics models. Probing the edge of the universe isn't just about distance. It's about time and history. It's about finding the oldest light and the first signals from the beginning of everything. The faint glow of the CMB is one of our best tools. It fills the entire sky, and by studying it in detail, scientists can map tiny variations that tell us what the early universe was like. But even this light only takes us so far. Beyond it lies a time before light could travel freely, a period called the Cosmic Dark Ages. Going beyond that barrier is a major goal for astronomy, but it's incredibly difficult. Some think that by studying gravitational waves, we might eventually peek even farther back. Instruments like the James Webb Space Telescope are designed to look at the earliest galaxies, the ones that formed only a few 100 million years after the Big Bang. Each discovery pushes the boundary of the known universe a little farther, but no matter how advanced our tools become, there will always be a horizon we can't cross. The speed of light and the age of the universe place limits on what we can observe. We might someday know more about what's just outside that limit, but there will always be more beyond it. There's a strange comfort in knowing that the universe is larger than we can ever see. It means there will always be more to wonder about, more mysteries just out of reach. The horizon of the observable universe acts like a moving target. As time goes on, light from more distant regions will have time to arrive here on Earth, slowly expanding what we can observe. But even as that happens, other parts of the universe will drift beyond our reach forever, pushed away by the expansion of space. Some galaxies we can see now will eventually disappear from view completely, as if they were never there. Exotic compact objects, beyond neutron stars and black holes. Somewhere between the end stages of a massive star's life and the creation of a black hole or a neutron star, there might be other exotic objects hiding in the shadows. These aren't just wild guesses. They're ideas born from gaps in our understanding and hints from unusual observations. They are known as exotic compact objects. Normally, when a very large star runs out of fuel, gravity takes over. The core collapses. Depending on how massive the star was, it can either stop at the neutron star stage or keep going and form a black hole. But what if there are other ways for matter to behave under those extreme conditions? Some theories suggest that certain types of matter could create stable objects even denser than neutron stars, but without becoming black holes. One of the most talked about ideas is something called a quark star. To understand this, it helps to know what happens inside a neutron star. In these stars, gravity squeezes the core so tightly that atoms break down. The electrons and protons combine to form neutrons, which is why it's called a neutron star. But what if the pressure keeps increasing? The neutrons themselves might break apart into smaller pieces called quarks. Quarks are the building blocks of protons and neutrons, and under normal conditions, they're never found alone. But in the heart of an ultra-dense object, some scientists think quarks could roam freely, creating what's known as quark matter. If that happens, the star could become a quark star, a ball of free quarks packed so tightly together that it might look almost like a single giant particle. If quark stars exist, they would be nearly as dense as black holes, but they wouldn't have an event horizon. That means, in theory, quark stars could be seen if we knew what to look for. They might be hotter than typical neutron stars or give off slightly different kinds of radiation. But so far, it's difficult to say for sure if any of the strange stars we've observed are actually quark stars. It's possible they exist, hiding in plain sight among the neutron stars we already know about. Some have proposed even more unusual objects called boson stars. Unlike ordinary stars made of regular matter like atoms, boson stars would be made of hypothetical particles called bosons. These particles are different from the matter we're used to. They can stack up in the same place without pushing each other away, which allows the possibility of forming incredibly compact objects. Boson stars could be massive, like black holes, but they would behave very differently. For instance, they might not have a solid surface. Instead, they could be giant clouds of quantum particles bound together by gravity. If they exist, they might explain some of the strange gravitational effects we've seen in space where no obvious black hole or galaxy seems to be present. There are also more speculative ideas like gravastars. These objects are thought of as an alternative to black holes. Instead of collapsing all the way into a singularity, a point of infinite density, some theories suggest that a collapsing star might stop just short, forming a shell of ultra-dense energy surrounding an empty void. From far away, a gravastar might look just like a black hole. It would still bend light and pull on nearby objects with incredible force. But inside, the structure would be very different. Instead of a singularity hidden by an event horizon, a gravastar would have a sort of bubble of exotic energy, keeping it from collapsing completely. Some researchers wonder if, under the right conditions, dark matter could clump together and form stars made entirely of this unseen material. These dark matter stars wouldn't shine like normal stars, and they might only be detected through their gravitational pull or the way they influence nearby gas and dust. For every neat category we've created, planet, star, black hole, there might be dozens of others we've never even imagined. And every time we build a better telescope or come up with a new way to analyze data, we might catch a glimpse of something that doesn't make sense, something that doesn't quite fit. These moments of confusion are often where the most exciting discoveries begin. There have been fast bursts of radio waves, sudden flashes of high-energy light, and gravitational waves that don't match the typical patterns from colliding black holes or neutron stars. Could some of these signals come from quark stars smashing together, or boson stars falling apart? It's hard to say. But as our tools get better and our understanding grows, we're getting closer to finding out. Mirror universes, exploring the possibility of a parallel cosmos. A mirror universe doesn't mean there's another world with copies of you and me living backward lives. Instead, scientists use the term mirror to describe a universe that might reflect certain features of ours but with key differences. The basic idea is simple. What if, at the moment of the Big Bang, not just our universe was created, but another one too? This other universe could be linked to ours, sharing some properties, but remaining invisible to us because it interacts in ways we can't detect with our current tools. There are some observations that don't quite line up with what the math says should happen. For instance, the universe seems to be expanding faster than expected. This is a puzzle scientists have been working on for years. Some have suggested that perhaps the pull from a mirror universe, with its own version of gravity or dark energy, could be affecting the way ours behaves. Another reason scientists are interested in mirror universes has to do with particles. In physics, particles have properties like mass, spin, and charge. And for every particle we know, there is supposed to be an opposite particle called an antiparticle. But when we look closely at the universe, we don't see as much antimatter as we expect. If the Big Bang made equal amounts of matter and antimatter, where did all the antimatter go? It could be in a mirror universe, completely separated from us but still connected in some hidden way. Some experiments try to detect particles that disappear without explanation. If a particle vanishes and doesn't leave behind the usual evidence of decay, maybe it's slipped into a mirror universe. Other tests involve looking for small changes in the behavior of particles that shouldn't happen unless there's something else, something unseen, tugging on them. In the lab, scientists can trap free neutrons and watch how long they last before breaking down. But results from different experiments don't always match. Some researchers wonder if these neutrons are secretly changing into mirror neutrons, particles that are exactly like regular neutrons but belong to a mirror universe. If true, this could mean there's a whole set of mirror particles out there, forming mirror atoms, mirror stars, and even mirror galaxies. Dark matter might actually be made of mirror particles from a parallel universe. These particles would pass through our universe, invisible and nearly undetectable, but their combined gravity would still pull on the things we can see. If mirror universes exist, they might offer answers to why our universe has the exact properties it does. Why is gravity so weak? Why do particles have the masses they do? Maybe the answers aren't in our universe alone. Maybe we are just one half of a larger twin system, with a mirror cosmos balancing out the scales. Some mirror universe theories even suggest that time itself could behave differently in these parallel worlds. There are ideas where the mirror universe runs backward compared to ours. That means as we move forward in time, the mirror universe rewinds, heading in the opposite direction from the Big Bang. In such a case, both universes might have been born from the same event, but instead of expanding in the same way, they mirror each other's progress through time. Time has always been a difficult concept in physics. Our laws of nature don't seem to care which way time runs. Most processes can happen forward or backward, but in real life, we only experience time going one way. Could it be that the balance comes from another universe? One where time flows the other direction? Unlike some concepts that remain locked in the realm of pure thought, scientists are working on real experiments that might reveal hints of these hidden worlds. They are looking for small anomalies in particle physics. They are analyzing the shapes of galaxies, watching for tiny differences that could hint at an invisible influence from somewhere else. Wormholes, natural bridges through space-time. In the simplest terms, a wormhole is a shortcut. Imagine the universe as a giant flat sheet of paper. If you draw two dots far apart on the paper, the shortest distance between them is usually a straight line. But if you fold the paper so those two dots touch, suddenly you have a much shorter path. A wormhole would work a bit like that, bending space-time so two faraway points are suddenly connected through a hidden tunnel. The question is whether the universe has created these strange bridges all by itself. The math behind wormholes has been around for a long time. In 1935, Albert Einstein and another scientist named Nathan Rosen came up with the idea. They imagined a tunnel that connects two black holes. Back then, they didn't call them wormholes, but the basic idea was there, a kind of bridge through space-time, created by intense gravity. Over time, this idea became more detailed. Scientists started to wonder if wormholes could actually exist, not just on paper, but out in the real universe. Could nature build them, or are they only something that works in theory? When people picture wormholes, they often imagine a circular hole floating in space like a glowing doorway that leads somewhere else. The entrance would be easy to spot, and if you flew your spaceship through it, you'd come out light years away in seconds. But if wormholes exist, they probably wouldn't look like that. They'd be invisible, hidden within the fabric of space itself. You wouldn't see them with your eyes, but you might notice the way they tug on nearby stars and gas clouds. Their gravity could reveal them, just like how we can find black holes by watching the things they pull around. If natural wormholes are real, they may not be stable. The problem is that spacetime wants to snap back into place. A wormhole is like stretching a rubber band. If you let go, it quickly goes back to its original shape. Unless something holds the tunnel open, the wormhole would close almost instantly. Scientists think you'd need a very strange kind of material called negative energy to keep it open. Negative energy isn't something we can make easily. It's not like gasoline or electricity. It's a strange concept from quantum physics, and we're still trying to understand if it even exists in amounts big enough to use. Maybe just after the Big Bang, when everything was chaotic and full of energy, wormholes formed by accident. Some theories suggest tiny wormholes could have popped into existence back then, smaller than an atom. Over billions of years, some of them might have stretched out and become larger. If any of these ancient wormholes are still around today, they could be hiding somewhere in deep space, connecting places we can't even imagine. Right now, even the closest stars are so far away that it takes years for light to reach us from them. Our fastest spacecraft would take tens of thousands of years just to leave our neighborhood. But with a wormhole, distance wouldn't matter in the same way. If there's a wormhole near Earth with its other end near a faraway galaxy, you could jump across the universe in moments. It wouldn't break the rules of physics either. You wouldn't be going faster than light through normal space. You'd just be taking a shortcut through a secret tunnel. Of course, there's no proof that these tunnels are out there. We've never found one. We haven't even found signs of the negative energy needed to keep a wormhole open. But scientists keep looking because the idea of one is so enticing. If wormholes do exist, they might help us understand things like dark matter or dark energy. Maybe wormholes play a role in how galaxies are connected. Even if wormholes are real and large enough to enter, traveling through one could be dangerous. The forces inside could be extreme. Imagine flying into a tunnel where gravity is pulling on you from every direction at once. Your ship might stretch and squeeze until it breaks apart. And what if the wormhole collapses while you're inside? That could trap you in a space where time and distance stop working the way we expect. These are problems we don't yet know how to solve, but they are important to think about if we ever hope to use wormholes for real journeys. Some theories suggest that wormholes could connect not just two places in space, but two different times. If that's true, a wormhole could act like a time machine, letting you travel to the past or future. This raises all kinds of difficult questions. What happens if you go back in time and change something? Could the universe even allow that? Right now, these are questions no one can answer, but wormholes are one of the few things in physics that seem to make time travel at least possible on paper. Axions and dark photons, the hidden messengers. Most of the mass in the universe is invisible. We call this hidden mass dark matter. But what dark matter actually is, that's still a mystery. This is where axions and dark photons come in. Axions were first proposed decades ago, not as dark matter, but as a way to solve a problem in physics dealing with tiny particles and the forces between them. But over time, scientists realized axions might do double duty. Not only could they help explain odd behavior inside atoms, but they might also make up dark matter. If axions are real, they are incredibly light and weak. Billions of them could fill every part of space, and we would never notice. They wouldn't push or pull on us in any normal way, but they might have just enough influence to explain why galaxies stay held together, even when there doesn't seem to be enough visible mass to make that happen. One of the reasons people find axions so interesting is because they come from math that already makes sense in other areas of physics. Axions weren't dreamed up just to explain dark matter. They seem to fit naturally into other parts of how we think the universe works. This gives them a kind of built-in credibility. If we ever find axions, it will feel like solving two problems at once. But finding them is the hard part. Because axions don't shine and barely interact with anything, they are almost impossible to catch. To look for axions, scientists have built special tools. One idea is that axions might be able to turn into light under the right conditions. By setting up strong magnetic fields and ultra-sensitive detectors, researchers hope that a few axions passing through might transform into a tiny bit of radio waves or light waves. It's like setting a trap, waiting quietly, and hoping that something invisible trips it. So far, no clear sign has shown up, but the search continues, with experiments growing more precise every year. Dark photons are an alternative idea. Regular photons are what make up light. Every beam of sunlight, every glow from a flashlight is made of photons. Dark photons would be their hidden cousins. But instead of carrying light, we can see dark photons would belong to a shadowy part of the universe, a kind of invisible light that only affects the dark side of things. Just like how regular photons carry the force of electromagnetism, dark photons might carry forces inside the dark sector of the universe. The dark sector is a way to imagine that everything we see, the stars, the planets, even people, is only half the story. There could be a whole other set of particles and forces interacting with each other in a shadow world we can't touch. Dark photons would be the messengers in that shadow world, helping dark matter particles push and pull on each other while barely doing anything in our visible universe. Some scientists think dark photons might not be totally cut off from us. There might be a tiny connection, a sort of leak between the dark world and the regular one. If dark photons can mix even just a little with regular photons, they might leave behind clues we can detect. These clues could show up in very sensitive measurements of light, or in experiments where particles don't behave quite the way we expect. It would be like hearing a faint whisper from a room you thought was completely sealed off. The idea of dark photons is exciting because it opens up the possibility that dark matter is not just made of lonely particles floating through space. Instead, dark matter could have its own rich and complicated story. There could be dark atoms, dark stars, maybe even dark galaxies, all interacting through dark photons. While these structures would be invisible to us, they might have formed alongside the galaxies we can see, shaping the universe in ways we are only starting to imagine. Right now, there are several experiments trying to pick up signs of dark photons. Some look at the way stars lose heat. If dark photons exist, stars might cool down faster than they should, leaking away energy into the dark sector. Others are using particle accelerators to smash things together at high speeds, watching for unexpected results that might hint at dark photons sneaking into the action. Just like with axions, no one has found anything certain yet. But the hints and whispers keep people looking. Maybe years from now, one of these strange particles will finally reveal itself. When that happens, it won't just answer old questions. It will raise entirely new ones, making us wonder what else is out there just beyond the edge of what we can see, whispering in the dark. Variable constants. Could the laws of physics evolve over time? The speed of light, the pull of gravity, the strength of the forces that hold atoms together, these are seen as the unchanging rules of nature. Scientists call these constants, and they are thought to stay the same no matter where you are in space or how much time has passed. This gives people a sense of stability, as if the whole universe is built on a strong, unshakable foundation. But what if that foundation isn't as solid as we thought? What if the constants themselves are not so constant? Imagine if the strength of gravity was just a little bit different billions of years ago. Even the smallest change could have made a huge difference. Stars might have formed in different ways. Galaxies might have spread out or clumped together in patterns we can't quite explain. And perhaps there are small signs of this hidden in the light from distant galaxies or in the way ancient stars behave. These are the kinds of clues scientists are searching for. One of the first hints that constants might not be fixed came from looking at something called the fine structure constant. This number controls how strong the force is between charged particles, like the ones inside atoms. It helps decide how atoms hold together, how light is absorbed, and how stars shine. If this number were even slightly different, the entire universe would look nothing like it does today. So scientists have carefully studied the light from galaxies billions of light years away, searching for any sign that the fine structure constant might have been different long ago. In some cases, they have found tiny shifts in the patterns of light, like a shadow of change from a time when the universe was much younger. The evidence is still debated, but it raises an unsettling question. If one constant can drift over time, what about the others? Another important number is the gravitational constant. This is the number that tells us how strong gravity is. Gravity is what pulls planets around stars and keeps galaxies from flying apart. If gravity was stronger in the past, the early universe would have collapsed more quickly into clumps of matter. If it were weaker, galaxies might never have formed at all. Some scientists have wondered if gravity might slowly weaken as the universe gets older. If that's happening, we might see galaxies moving apart faster than expected, or stars burning out sooner than they should. So far, gravity seems steady, but the search for small changes continues. Right now, the speed of light is believed to be the ultimate speed limit in the universe. Nothing can go faster. It's a central part of how time and space work. But what if, billions of years ago, light traveled just a little faster than it does today? Some theories suggest that this could solve a few cosmic puzzles, like why the universe looks so smooth and even in every direction. Maybe, in the earliest moments after the Big Bang, a faster speed of light helped spread energy more evenly across space. It's also possible that the constants are different in other parts of the universe. Some scientists think that what we see here might just be one region in a much bigger multiverse. Maybe each part of this larger reality has its own set of constants. In one area, gravity is stronger. In another, atoms are held together by weaker forces. Maybe some of these places are too strange for stars or planets to form, and maybe others are almost exactly like our own, with only the smallest differences. If that's true, then the constants we know might not be special at all. They might just be the numbers that happen to work out in our little corner of everything. There are some who wonder if the universe itself is learning in a way. As it expands and cools, as stars are born and die, maybe the very structure of reality is slowly adjusting. New particles could appear, old forces could fade, the constants could be responding to the shape and state of the cosmos itself. It's a wild thought, but it's not impossible. Finding out whether constants change is extremely hard. These numbers don't shift quickly if they change at all. The changes would be slow, stretched over billions of years. But scientists keep finding clever ways to look. They check the light from the most distant galaxies, which shows us the universe as it was long ago. They study the oldest stars and measure how they burn. They look at the leftover glow from the Big Bang. And each of these tests brings us closer to an answer. If constants do change, even just a little, it could explain some of the biggest mysteries in space. Maybe it's why the expansion of the universe is speeding up. Maybe it's why some galaxies behave in ways we don't expect. For all the stability we thought the universe had, we may find that its deepest laws are just part of a bigger, shifting story. The rules we thought were set in stone might be more like moving targets, gently changing as the universe itself grows and changes. Entanglement at the edge, quantum connections across vast distances. In the world of quantum physics, there is an idea called entanglement. When two particles become entangled, something strange happens. No matter how far apart they are, they seem to stay connected. If you change something about one of them, the other reacts instantly, as if they are linked by an invisible thread that stretches across any distance. This happens faster than light can travel. It doesn't seem to matter whether the particles are next to each other or on opposite sides of the universe. Somehow, the connection stays. At first, this sounds like it should only happen in tiny labs with tiny particles. Scientists have tested entanglement with things like electrons and light particles called photons. The results have been clear. Entanglement is real. But what if this strange link isn't just something that happens on the smallest scales? What if it also happens across the cosmos? Could two particles be entangled from opposite sides of the galaxy? Could entire regions of space be connected by hidden quantum threads that we cannot see? If entanglement works the same way across large distances as it does on small ones, then the universe might not be as separate as it appears. Stars, galaxies, and even clusters of galaxies might be quietly sharing information with each other through connections we haven't yet found. It's as if the universe could have a secret communication system built into its very design. Galaxies tend to form in large web-like patterns. When we map out where they are, they don't appear scattered randomly. Instead, they group together in long strands that stretch for billions of light years. These strands cross and twist into what looks like a giant cosmic web. Could entanglement help shape these patterns? Maybe the galaxies at opposite ends of a strand are still linked in some unseen way, following rules that connect them across the emptiness. Some galaxy clusters appear to drift together, as if something far away is pulling them. We don't know what is causing this. and some scientists wonder if invisible quantum connections might be playing a role. Of course, these ideas are still guesses. Nobody has proven that entanglement works on such big scales, but the possibility has caught people's attention. Another question is whether the early universe itself was built on entanglement. Right after the Big Bang, everything was incredibly small, hot, and close together. If particles were entangled back then, and if that entanglement lasted as the universe expanded, then maybe some of those ancient connections are still around today. Hidden in the CMB, there could be clues about how the universe grew and stretched while keeping parts of itself secretly connected. When something falls into a black hole, its information seems to disappear. But many scientists believe the information isn't lost. It's stored on the surface of the black hole, mixed with the particles that escape as radiation. Some theories suggest that entanglement is what allows the information from inside the black hole to stay connected with the particles that escape into space. If that's true, then black holes could be like giant entanglement machines, tying distant parts of space together through invisible links. And then there's the wildest idea of all. What if space itself is made out of entanglement? Imagine that instead of space being just empty nothingness, it is held together by quantum connections. These invisible ties would link not only particles but also entire regions of space. In this view, the distances we see between objects are not as important as the hidden connections beneath them. It's as if the whole universe is woven from threads of entanglement, and the fabric of reality itself is built on these links. Some researchers are studying the way particles move across huge distances. Others are looking at how the energy of the universe is spread out. There are even experiments being designed to see if we can detect signs of cosmic scale entanglement by looking at very faint signals coming from deep space. These experiments are difficult. The universe is big and entanglement is fragile. But if we could find proof, it would change how we see everything. If the universe is connected by entanglement, then the old idea of distance starts to lose its meaning. It wouldn't matter if two things are right next to each other or separated by billions of light years. The connection would still be there. And if the whole universe is built from these connections, then we are part of that too. Every atom in our bodies, every breath we take, could be quietly linked to something on the far side of the cosmos. This would mean we are not just living in the universe. We are woven into it, tied to its deepest structure. Exotic matter. Could the unseen reshape cosmic evolution? Matter takes familiar forms. There are the things we can see and touch, stars, planets, gas, and dust. Then there's the unseen matter, like dark matter. But even beyond these, some scientists wonder if the cosmos holds something stranger still. What if there are entirely different kinds of matter out there? Matter so exotic that it doesn't follow the rules we expect. Exotic matter isn't something we found in a lab or observed in the sky. It's not part of the familiar table of elements or anything we can easily describe from experience. Instead, exotic matter comes from theories that try to answer some of the biggest mysteries about how the universe works. These theories suggest that exotic matter could have properties unlike anything else. It might have negative mass, which means instead of being pulled by gravity, it would push away from other objects. It could have unusual forms of pressure or energy that behave in ways no ordinary material does. Exotic matter with negative energy might be able to keep the throat of a wormhole stable. Some researchers think that exotic forms of matter could be acting like dark energy, pushing against the fabric of space and causing this cosmic acceleration. If true, exotic matter wouldn't just be some odd material tucked away in rare corners of the universe. It would be everywhere, woven into the very structure of space, quietly influencing how the universe grows and changes. Right after the Big Bang, conditions were extreme. It's possible that during these early moments, exotic forms of matter appeared, even if only for a short time. These unusual materials might have driven rapid inflation, smoothed out the chaotic beginnings of the cosmos, or left behind subtle imprints we can still detect today. In certain theories, stars might collect exotic particles in their cores. Over time, this hidden material could change the way the star burns its fuel, lives out its life, or even how it ends. Instead of becoming a white dwarf, neutron star, or black hole in the usual way, an exotic matter-filled star might collapse into something entirely different. Some theories suggest entire objects made out of exotic matter floating through the cosmos. These could be stable, long-lasting lumps of strange particles, traveling through galaxies without interacting much with normal matter. If they exist, we might not have noticed them yet because they wouldn't give off light or energy in familiar ways. Instead, they would quietly pass through the universe, their presence only detectable through tiny gravitational effects or rare, subtle collisions with ordinary matter. Some speculate that exotic matter could make things like stable wormholes, warp drives, or even artificial gravity possible. Right now, these ideas belong more to science fiction than science fact. But history has shown that sometimes yesterday's impossible ideas become tomorrow's breakthroughs. Scientists are developing experiments to search for clues. So far, we haven't found anything definitive. But the search continues, driven by the idea that somewhere in the unseen parts of the universe, exotic matter might be quietly at work. The universe has surprised us before. Just a few decades ago, dark matter and dark energy were only theoretical ideas, and now they are some of the biggest parts of our understanding of the cosmos. Exotic matter, if it exists, could be the next big surprise. Which phenomena has fascinated you the most? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.